Hey there, everyone, it's Alejandro, and welcome back for day 192 of me doing daily code challenge that there is 1 year's worth of green contributions here on GitHub. So today's problem is for January 24th, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode medium problem 802, find eventual safe states. There is a directed graph of n nodes with each node labeled from 0 to n-1. Okay, a graph problem. The graph is represented by a 0 index 2D integer array graph, where graph of I. Okay, 2D integer array graph. Okay, so like an adjacency matrix. Graph of I is an integer array of nodes adjacent to nodes of I. Oh, no, it's not. Oh, okay, it's 2D. Okay, so it's like an adjacency list, not an adjacency matrix. So it's like, I thought it would be like, IJ means there's an edge between nodes I and J. Okay. Of nodes adjacent to node I. So, okay, meaning there's an edge from node I to each node in graph of I. So, yeah, so graph, so it's an adjacency list of length n. Where each index I is essentially ith node's neighbors. Okay, a node is a terminal node if there are no outgoing edges. Okay, so if it has an out degree of 0. A node is a safe node if every possible path starting from that node leads to a terminal node or another safe node. So basically, as long as there's no cycles. Okay, return an array of all the safe nodes of the graph. The answer should be sorted as in ascending order. Okay, one way immediately of doing this problem, go for every node, run a DFS, see if you end up terminating without cycles. There you go, bada bing, bada boom, right? There's probably a more efficient way of doing things, right? Where it's like, actually, yeah. So what if you start off with like, a set of every node or even like a queue of every node if you do like a multi-source BFS. And you essentially say like, okay, we're going to try to go through everything, kind of like in a DP mindset where it's like, if I go to a neighbor, it's like, okay, if it's a terminal state, great. Otherwise, we'll check if that guy is also a safe node, right? And if that one is not a safe node, then you yourself are not a safe node, and blah, 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 right? So if anything, we could do a topological ordering on the nodes to essentially figure out how to traverse the nodes, right? Ooh, we could do. It's almost like DP, right? Where it's like I'm thinking not in terms of like legitimate DP, but in terms of like why you could even do this as DP, right? Where it's like, okay, for each neighbor, if like, okay, for example, like a node, we can consider nodes good or bad, right? So it's like if you have an edge to a bad node, that means it's like you're bad yourself. Otherwise, if all your neighbors are good, then it's like this is good, right? Now the only problem is that, like, yeah, in the case where there are cycles, you don't form a DAG, right? Where it's like if you point yourself or you point yourself back, it's like that's pretty bad, right? Yeah. It's just, yeah, what would be nice is essentially as you do a DFS, no, if there's a cycle in a component, every node in that component is bad, right? If A points to B, B points to C, C points to D, D points to A. It doesn't matter where you start in that cycle. What if, yeah, B points to C, then it's like there's A to D is bad. A to C is good. Yeah, so it's like, if A points to B, C points to D, points to A, there's a cycle here, right? But if this points to F here, that's like here there's a cycle, but F itself ain't bad. Okay. What are the constraints on this? Ooh, n is 10 to the 4th. So I actually can't do things badly. I can't do n squared. So I can't go through n of the nodes and then just do like a DFS from there. That's interesting. So there will be some element of not recomputing work. Yeah, number of edges is at most the number of the nodes times 4. Yeah, this is interesting, right? So example 1. 2 is good. 2 has an out degree of 0 in the first place. So it's like you gotta ask yourself, right? So if I look at something like 0, it's like, okay, it has no out degrees, it's a good node. Then I look at something like 1, okay, it has something to 2 and it has something to 3. So are 2 and 3 good? But it's like, okay, in this case, I'm lucky that neither 2 or 3 point back to 1, right? But that's the annoying case, right? 1 points to 2 and 2 points to 1, and I'm not, like I can't assume that this forms a DAG. The whole point is that this might not form a DAG, and that is why some nodes might be bad. Yeah, no outgoing edges. It is a safe node if every possible path from that node leads to a terminal node. Right, where it's like, if anything, I can topologically sort the elements, right? Where it's like I can go backwards from, like, ones with that topologically sort. But if I topologically sort, I sort them based on their in degree. What if I want to topologically sort based on out degree? Which is weird, which is very weird. Right, or is this one of the, what if we invert the graph, right? What would this turn the problem into? A node is a terminal node if it has no outgoing edges. So what if it had no incoming edges? Oh, wait. What if we inverted this problem? What would it turn the problem into? It's kind of hard to think about. If I inverted this problem, what would it become into? It's kind of hard to think about, right? Then it would be, it's not necessarily if it has n-1 incoming edges, right? No. Right here, 0, 0. Yeah. Yeah, it's a little hard to think about. Because if I flipped all the edges, right? It'll be very interesting. Actually, 0 points to 1. 1 points to 2 and 3. If I topologically sort based on that degree, right? Ones with a 0 out degree are terminal nodes. First, actually, that might probably be the right path, right? Because then it's like, okay, if I have 0 terminal nodes, then it's like, okay, I know that there's nothing to go off of, right? Oh, would it be as simple as like a topological sort based on the out degrees, and whatever I get at the end of the day are all the ones? Wait, that might legit be it. Right? Because it's like topological sort is great for cycle detection in the first place. And the point is I won't be able to get the full topological sorting because of cycles in the graph. Let me think here. Do I want to do a visit set when you do topological sort? No. I just pop nodes and go through. Yeah, let's do something. Idea. Topologically sort the elements based on their out degree, not their in degree, as in typical topological sort algorithm. Typical topological sort algorithm. Then we'll start off with our set with 0 outgoing edges, making them terminal nodes. Wait, let me think. This is no outgoing edges, so it's a terminal node. But this is sort to think about. Maybe it's not that simple. This is 0 outgoing edges. This is 1 outgoing edge. So, yeah, no. But this is good because it needs to be that I need to check, is this safe for terminal, right? Can I rely on the fact that because I'm topologically sorting and going in reverse order of like from smallest to largest initial out degrees, and it's like by the time that I look at like something's outgoing edges, I can then check like, okay, because what if what if two nodes have the exact same amount of outgoing edges, right? Does that become problematic? 1, 2. Usually the examples are telling, right? Only 4 is a terminal node. Wait. Yeah, just the only thing for something like this is that you can't do DP where it's like, you check, it's like, okay, am I safe? It's like, okay, are all my neighbors either safe or terminal and so on? Because again, it's like what you may rely on someone that relies on you and so on, so it does not form a DAG. So DP is out of the question. Some smart idea with topo sorting would be kind of cool. Here it obviously start with like 6 or 5. So 6 has 0, 5 has 0, 4 has 1. Right, the point is that I do 5 before I do 4, so I'd be chilling, right? Because I already have said like, oh yeah, 5 is terminal. So you're chilling. So when you look at 4, you're chilling. 3 has 1 outgoing edge. So let's mark these. It's like almost like a dictionary, right? So 6 maps to 0, so it's terminal. 5 maps to 0, it's terminal. 4 maps to just 1. 5, we'll say empty list. Empty list. Here we'll say 0, 0, just in case it wasn't clear. 3 maps to just 0, which is 1. 2 maps to 5. 1 maps to what? 1 maps to a crazy amount of things. It maps to 2, 3. That's it. Why does it feel like there's so many arrows? Okay. Which is a total of 2. Right? And 0 maps to 1. And it maps to 2. Did I get everything? I think so, right? 3 maps to 0. Yeah, okay. Okay, when I write it down like this, it doesn't seem that exhaustive. Here, it just feels like there's a million arrows, right? But the point is that, like, I'd be like, okay, 6 is terminal, 5 is terminal. That's like, when I look at 4, it's like, okay, then I'd look at the 1s, right? Yeah, here's the problem. So here, I'd be looking at 0 before I've even checked if it's terminal or not, right? So yeah, for something like 4, we're chilling. For something like 2, we're chilling. But here, when I gotta look at 0, 0 comes later in the topological ordering here. Actually, this is just this. Really, it's like, it's almost as if though this is, yeah. It's one of those cases where we do invert the graph. I'm not, here. Yeah, this is very interesting, extremely interesting. The point is that here it's like, yeah, because then I dock everything that was dependent on 6 by 1. Which really means I want to say like, hey, yeah, okay, topological sort only makes too much sense here. I'm probably going to need to use it one way or another. Now here's the thing, when I say 6 is a terminal node, I'm like, okay, anything that points to 6, you're chilling, my friend. Same thing for 5. It's like you're chilling. You're completely chilling. So anything that was pointing to 5, you're chilling. So then these become zeros. Yeah, the point is that 3 wouldn't become 0 yet. Right, so then I do 4 and 2. Right, so the point is that I'd have this, right? I have top of order. And here we'd have, you know, we're like 6, bro, you're chilling. We got 6. And everything that pointed to 6, right? Yeah, so here we'll remove it. Now we've got 5, and you're chilling. Anything that points to 5, we'll get rid of 5. This becomes 0. This becomes 0, and we'll get rid of 5. Then 4, you're chilling. You get 4. Anything that points to 4, nothing here. So there you go. 2, you're chilling. We'll add 2 in here. Anything that was pointing to 2, like these guys. Like these guys. You're chilling. And now here you can't make any more work. But yeah, 2, 4, 5, 6 is the actual answer. Okay, I think that's literally, yeah, it's enough. All right. Okay. Seems promising, so we'll try it out. Then we'll start with our set of nodes with 0 outgoing edges, making them terminal nodes, and loosening the constraint for any nodes that point to 6. Loosening. Hence, the first step of the algorithm will be to create a hash map of nodes to such list of nodes that point to them. Right, so here's 0 points to 1, points to 1 and 2, but we want, okay. Node 2 in neighbors. It was a hash map. For I in range, length of graph. Here we'll say default tick of list. We'll say here we want in neighbors. Nay in graph of I, node comma neighbors in enumerate graph. In neighbors in neighbor. So node 2 node in neighbors. D equals it's like a reverse adjacency list. A reverse adjacency list. D of nay dot add. We'll make this a set. Dot add node. Right, printf string D equals and return an empty array right now. So yeah, so 1 is pointed to by 0. 2 is pointed to by 0 and 1. 1 points to it, 0 points to it. 3 is pointed to by 1. Good. 5 is pointed to by 4 and 2. Good. 0 is pointed to by 3. This is good. This is good. This is very good. This is pointed by. I reverse see this. Okay. Noise, 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 noise. D. That point. Okay. Now we gotta do a topological sort, right? So here we'll do out degrees. Okay. Node. Degree of node equals 0. Okay. Here we'll say topo order should be given in ascending order. So here we'll return sorted topo order. Here we'll return topo order dot sort. There we go. Okay. Here we'll say while length of Q is greater than 0. Here we'll say node is equal to Q.pop left. For in neighbor in D of node out degree of in neighbor minus or equal to 1 if out degree of in neighbor equals 0 and Q dot append in neighbor. Topo order dot append node. Okay, does this work? Okay, that's accepted. Let's submit. And there we go. Completion streak 192 days. Consistency is key. See ya tomorrow. Okay, a nice little topological order graph problem to get us started through the end of the day. Feels absolutely nice and wonderful. Okay, sweet, sweet. This was a nice little problem. Just think a little bit, get through the solution. There you go. Bada bing, bada boom. Life is nice. Okay. Okay, I wonder if we could do this a bit better. Well, okay, first of all, we could do set for in range length graph. Does this work? Yep. And here we'll say everything that says length of graph. Or is it only 2 spots? Lol. Okay. I was gonna replace this with n. And here say n equals length of graph. Okay, submit. Okay, that brings me a little bit closer to the standard deviation. So yeah, so this is the point of the problem where I try to make my stuff faster in terms of the O of 1 stuff. Yeah, I don't know if this is a time to use the walrus operator. Yeah, this can only, this is good, right? Or here, maybe I can make another optimization. Because I'm going to loop through everything anyways, right? So I might as well use a list. Yeah, maybe that makes things faster. Okay, 51 ms, we're 50.7%. Here we can even do something like while q. Maybe that makes things better. Okay, 47 ms. Here if I do q.pop, doesn't really matter the order at the end of the day, right? Yeah, so this doesn't really matter. Yeah. So here I don't need a collections.deck. So here we can have out degree where q equals this, or this. Append. Does that even make it go faster? Right, let's test. Not really. Or does this even make it go faster for range n? Node. Node in range n. Graph of node. Okay, maybe a little faster. Maybe here we can do this. Out degree comma q. Equal graph of node. Neighbors. Out degree. Length of neighbors. Out degree. Dot append degree. Q equals 0. Q dot append node. Right. Then that's no longer necessary. Yeah, still there. So yeah, so these changes don't seem to matter much. Node comma neighbors in enumerate graph either. Yeah, so I like to usually try to see if I can like, make the O of 1 stuff make our algorithm faster. Here doesn't seem to have much impact at all. Okay, maybe that makes things a little bit faster. That's nice. Here we'll call our queue, we'll really call it a stack. Yeah, this is the best I can do. This is pretty much the best that I can do. Okay, so this works. Let's submit. And there we go. Okay, so we're kind of like right dead center in the middle of this standard deviation curve. So you know what? That's very nice. Bada bing, bada boom. So as always in all my videos, I do a quick recap if I was able to solve the problem. So for this one, I kind of was able to recognize what to do pretty fast. The point is that basically you have what's called terminal nodes. A node is terminal if it has no outgoing edges, right? It's essentially terminal in that you can't do anything more for that node, right? If you think of like, you know, a node's available actions in terms of like, you know, the edges that it can go through. If a node has no edges, then it has like no actions from that node. So it's considered a terminal node. Now a safe node is considered safe if every single other node it points to, well, first of all, if it points to nothing, it's by definition safe, but it's really by definition terminal if it has no edges. But otherwise, if a node has edges, it's considered safe if and only if all of the nodes that it points to are either terminal or also safe. And by safe means like, you know, eventually like, you know, out of all the edges, like, you know, every single possible path that you can take from a certain node ends up leading to a terminal state, to a terminal node, I should say. And basically there's never any cycles and so on. And so whenever you think cycles and so on, like, you know, something like topological sort always kind of comes to mind. Although I don't think that's really the reason that I kind of came to mind. So at first I tried to frame this in terms of a dynamic programming problem where I was like, okay, it's like, you know, for a node, it's safe if and only if all of its neighbors are either safe or terminal. Obviously, checking if a node is terminal is very, very simple because it's just like, okay, this has zero outgoing edges. But the problem essentially comes from when two nodes kind of point to each other, right? Because if one node, like if you have like node 0, so does this mean, here I don't think there's any two nodes that point to each other, right? 0 points to 1, 2, 1 and 2 point to other things, right? Yeah, here I don't know if there's an example of two nodes that essentially point to each other, but you can imagine if two nodes point to each other, then essentially it's like, okay, you want to know if like, you know, all of your neighbors are safe or terminal, right? So it's like, let's say 1 and 2, let's say 0 and 1 point to each other, right? It looks like they point to each other even though they don't in this graph. But let's say 0 and 1 point to each other. Then it's like for 0, it's like, okay, it's like you're going to check is 1 a safe or terminal node, right? And then from 1, it's like, okay, it points to 0, so you're going to check is 0 a safe or terminal node, right? And so immediately you can see that the graph, it like, in terms of like, you know, problem dependency graph, it does not form a directed acyclic graph, right? Which is what you need in order to apply dynamic programming. So if it was a DAG, it would be very, very nice and convenient, but in this case, it's not really a DAG, right? And so you gotta find like, you know, a different way to find subproblems and topologically order them in a way where you are and end up with like, you know, a DAG to essentially solve, right? Now, one thing that came to my mind is when you topological sort a graph, right? Usually you do it based on n degrees, but the way that you know if there's a cycle in the graph is if essentially you are not able to complete your topological sort, right? If you try to topological sort using like, you know, the I forget what it's called, it's Kahn's algorithm or something. I think it starts with a K. That I do know, but I hope the name is Kahn. Otherwise, I'll probably look a little silly. But essentially, Cadane is something else. Okay. The point is that usually the algorithm is like you start off computing all the nodes in degrees. You start off with the ones that have a 0 in degree, and then it's like, okay, for every single one that you pop from a queue, that starting with the ones with 0 in degree, it's like, okay, everything that it points to, now loosen that constraint, and then if it's a 0 in degree, then essentially add it to the queue, blah, 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 blah. Here you'll see in this problem, I actually do the reverse. I do it by out degree, and we'll explain why, all right? But the point, now I'm forgetting what I was explaining, lol. The point is that, like, okay, there might be cycles in the graph, right? If there's a cycle in the graph, you know, it won't be part of our topological sort. That is a pretty neat side effect, right? Because that's essentially what the core of this problem comes down to, right? A node is safe or terminal, like, you know, if like a node is terminal if there's no outgoing edges, a node is safe if, like, you know, every single path from that node essentially leads to a terminal node, right? Essentially, if you DFS from that node, you'll never reach a case where it's like, you know, you reach a visited node again, right? That's kind of the point. Like, there will never be any cycles, right? If you reach a visited node again, that means there's some sort of cycle in the graph, right? And that was my immediate first thought, right? Like, run a DFS from every single node and like, realize what do you either end the DFS or do you at some point visit something you've already visited, in which case, it's not a safe node, right? Obviously, that would be like an n squared solution where it's like for every single node, you have to at worst traverse every other node, which would be very terrible, right? So obviously we did end up doing that, but like, that is kind of the naive idea. So really you can turn this problem in like, asking yourself like from a node, and I try to do a DFS, is there a cycle, right? Because if there is a cycle, then it's not a safe node. If there is no cycle, that means you visited every node you ended up traversing through, you only traversed through once, meaning you either ended up going to a terminal node in every single possible path, right? Which means that it is a safe node, right? So essentially this problem boils down to like, if you were to do a BFS from a node or a DFS or whatever, do you end up going inside of a cycle or not, right? And then obviously, again, a topological sort is really nice because it helps you find like, is there a cycle or not? And it's also convenient in that using this in-degree algorithm, that essentially the nodes that will be inside of your topological sort, if there's a cycle, you'll end up having less number of nodes than the number of nodes that there are on the graph, because again, you'll essentially ignore the nodes that are responsible for causing the cycle in the first place in the graph, right? The point is that like topological order is like, a topological order of the dependencies. If there's a cycle, they won't be part of the topological sort because it's like, for A you need B, for B you need C, for C you need A. So they're never able to ever enter like, an in-degree of zero state because they're all always depending on each other. So it's a very, very, very convenient side effect of topological ordering that here I was kind of able to leverage. But here, instead of topologically ordering based on in degrees, I do so based on out degrees. Why? Because a node with zero outgoing edges, i.e. a zero out degree, is what's considered like, an initial valid node, right? I like a safe / terminal node, right? Here I think of nodes in terms of good and bad. A good node is either terminal or safe. A bad node is not terminal and not safe. It's neither of those, right? So a good node is either terminal or safe. A bad node is like, neither of those. And so I want to start off with like, a bunch of good nodes. And so what good node should I start off with? Well, obviously what's very easy to check is like start off with all the nodes that are terminal nodes, right? The ones that have zero outgoing edges in the first place, right? And then when you find something like 6 or 5, then you say like, okay, I know that so 6, for example, has no outgoing edges, so it's a terminal node. So I can be like, okay, 6 is good. Now, anything that points to 6, I can know like, hey, you're chilling, right? Because if you point to 6, 6 is a terminal node, right? So for example, here a good example is 5. 5 has no outgoing edges, right? So we're chilling. 5 is a terminal node. So it's definitely a good node, right? Now for something like 4 here, we'll end up looking like, hey, it has one outgoing edge. And that one outgoing edge is to 5. But 5 is a good node, right? We already figured out that 5 is a good node. So we know that if 4 only has one edge, meaning it points to only one node, and that node is good, then 4 itself must also be good, right? That is kind of the point, right? Because again, a node is good if it's safe or terminal, i.e. if you ran a DFS from it, you'd end up reaching no cycles, right? And so obviously the way that you start is like you start with your terminal nodes, the ones that have no outgoing edges, and then it's like from there build up like, okay, anything that points to that terminal node that I just saw, that I know is a good node, I can say, it's fine if you point to this guy because I know it's good, right? So, and the way that we can do this is again with like a topological sort going in reverse direction, right? So start off with all the nodes that have an out degree of 0 because then you know that they're essentially good nodes, right? So that's exactly what I do. Here I have a tuple order is equal, by the way, here what we'll need to end up doing is like, for example, once I say 6 is good, cool, but there's no englobbing edges, so I don't do anything. Now when I say 5 is good, I want to say, hey, anything that points to 5, you're chilling when it comes to that connection, right? For example, here 2 and 4 point to 5. 2 points to multiple, actually, does 2 point multiple things? 0, 1, 2, 2 only points to 5, right? If it pointed to multiple things, that would also be okay. But the point is like here, like, 2 and 4 both point to 5. But once I've essentially finished my job with 5 and said 5 is a good node, I can essentially tell myself like, hey, this connection to 5 and this connection to 5 for 4 and 2, I can say, don't worry about it, bro. You're pointing to a good node. So that connection is good. You don't have to worry about it anymore, right? So that's kind of why topological sort is nice here. But in order to do that, I need to know for a specific node, if I know that a node is good, be like, okay, all the nodes that point to me, note that pointing to me is fine, right? So that's why I do at the very beginning. I essentially have a dictionary where for every single node, I'm going to grab a list of all the nodes that point to it, right? So I'm going to loop through every single node in graph, as well as the list of neighbors for that node, because the nodes are the indices and the values are the list of neighbors. That's just how it was passed into us. So here I'll say for each neighbor in neighbors, I'm going to say, hey, that node points to neighbor. So instead of the dictionary here, for neighbor, I'm going to append node. Why? Because node points to neighbor. So node is one of neighbors, like, in neighbors, right? It points to the neighbor. So again, we want to record for every single node the nodes that point to it. So I'm going to put into my dictionary here that represents nodes that point to me. So for neighbor, I'm going to say, hey, I'm going to append node because node points to me, i.e. neighbor, right? Here I'm also going to grab degree, which is the length of neighbors, because here I need to compute the out degree of every single node. So here's okay, the out degree of the node, obviously for example here this is the nodes that the node 0 points to, right? So how many outgoing edges are from 0? Well, however long is the length of the array of its neighbors that it points to, right? So here I grab the length of the neighbors. I say, okay, out degree of this node is degree. If the degree is 0, I will append it to my stack. Why do I append it to my stack? Because I'm going to start off with all the nodes that have an out degree of 0, because those are my terminal nodes, right? I'm starting off with my terminal nodes. Here I could even call my stack good nodes. Here is equal to this. Good nodes equals this. A node is good if it is terminal or safe. Terminal, hence good. Node is safe, hence good. There we go. And we can submit it just with that notion right there. And there we go, bada bing, bada boom, right? So just making that clear, right? So here it's like I essentially have my good nodes, and at the very beginning I'm going to start with my terminal nodes, because I know, again, a node is good if it's terminal or safe. So at the very beginning, if it has no neighbors that it points to, it is a terminal node. It has no outgoing edges, right? Then I'm going to have my topological order. So here I'm going to say, while I still have good nodes, I'm going to append those good nodes into my topological order. So here I'll pop a good node from my sorry, from my list of good nodes. I'm going to append that to my topological order, and then we're going to say, okay, for every single node that points to me as the good node, right? For example, for 5, I just said it's a good node. Every node that points to me, like 4 and 2 here, I'm going to say, hey, that connection that you point to me, you don't have to worry about it anymore. You are pointing to a good node. You're chilling, right? So here what I'm going to say is the out degree of that node, I'm going to subtract it by 1, right? Because let's say something like 2 here, let's say pointed to many things. It pointed to 0, 1, and 5. Okay, that's 3 things it's pointing to. We want to know if those 3 things are safe. Well, now we can get rid of one of them, right? Because let's say this is the pointing to 0, this is the pointing to 1, and this is the pointing to 5. Well, we can get rid of the pointing to 5 because we now know that, hey, 5 is a good node, so you're pointing to a good node, so you don't have to worry about this thing over here. If 0 happens to be a good node and 1 happens to be a good node, then 2 is a good node, right? In this case, 2 is only pointing to 5, so when we see that 5 is a good node, that's the only dependency. Its out degree will be 0, so everything it points to will now essentially be good nodes. So we can say, okay, it's a good node, let's append it to our good nodes list, right? That way, everything that points to it, when we pop that guy, will also be have that dependency removed. But the point is that it's essentially topological sort, just with out degrees instead of in degrees, right? And so that way, it's like we start off with our terminal nodes. Every single node that points to that terminal node, we're going to say, hey, that edge to the terminal node, you can essentially ignore it. So we're going to subtract the out degree of that, incoming node by 1. And then if the out degree is now 0, that means it's like, okay, essentially, it used to have an out degree that was larger than 0. And we essentially subtracted by 1 enough times because all of its edges end up pointing to good nodes, right? Which makes the node itself good, right? It'll be a safe node. Every node that it points to is either safe or terminal, i.e. it points to only good nodes, so it itself must be good nodes, right? Because if you are a node that points to other safe nodes, let's say, if you point to a terminal node, it's obvious, right? The path of you going from a node to that terminal node, well, it terminates right there, right? Otherwise, if you point to a safe node, by definition of that node being safe, all the paths from that safe node onwards all terminate. So if you point to a safe node, by definition of that node being a safe node, all paths from that safe node terminate. So if you point to a safe node, you're also good, right? So if all you point to are safe nodes and terminal nodes, i.e. good nodes, you yourself are also safe/terminal, i.e. you're also a good node. So if at some point we see that the out degree of a node, we made it 0, that's because it used to have non-zero out degree, because it pointed to a bunch of stuff, but now it's 0 because all the stuff that it pointed to, we figured out are all good nodes. So we say, oh, it must also be a good node. And we append that into our good nodes list here, because we're going to pop it again and essentially, like, say for, okay, since that node is also good, everything that points to it as well, we'll also, like, subtract the out degree of that node by 1, and then check again if that node is good, and so on, etc., 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 right? It's like a chain of events, right? Then essentially at the end of the day, we might not have all the elements that were originally on the graph, and that's totally okay. In fact, inside of the very first example, we'll have all the elements except we'll only have the elements in here, right? Because something like 1, essentially here it's 1, 3, and 0, right? So the problem with 1, 3, and 0 is that 1 points to 3, 3 points to 0, 0 points to 1. It creates a cycle, right? So no matter whether I start at 0, 1, or 3, since they're all part of the same cycle, no matter which node I start from, it'll always end up never terminating, right? Because again, like, from 0, here's a path, like, 0 to 1 to 3 to 0 to 1 to 3 to 0 to 1 to 3. It never leads to a terminal node or a safe node, right? It is a cycle. So it itself must not be a safe node. And same goes for 1 and 3, right? Because of the same overall cyclic path. The point is that there is a cycle. So they cannot be part of the set of good nodes, right? Safe/terminal nodes, right? So that's kind of the point. So again, this problem is really just cycle detection, which again, topological sort is great for, right? And the convenient side effect of topological sorting is that when there's a cycle in the graph, you won't have all the nodes because you won't have the nodes that are part of a cycle. By nature of it being that since they're in a cycle, they all depend on each other, so you'll never get to the case where you have, like, the degree being 0, where you can append them to the list of, like, good nodes in your topological order, etc., 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 right? That's kind of the point, but it turns out to be a super convenient side effect in cases like these, where, like, you only want, like, nodes that essentially, when you try to DFS from them, eventually lead you to, like, terminal states. You never revisit a neighbor that you've already seen before. So it's very, very, very convenient in that way. And then at the very end, when we have a topological sorting, we don't actually care about the topological sort itself. We just care about those nodes because they're the good nodes. And so here it says that they want the answer sorted in ascending order. No problem. We'll just sort the nodes in ascending order. Return those nodes in ascending order. There we go. Bada bing, bada boom. We have a nice and efficient solution to the problem. So that's pretty much it in terms of how I was able to solve the problem. And hopefully that solution makes sense. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So till then, ciao, ciao, my friend. Bye-bye.